let's go over the final 2 questions for the week. And here we start with evaluating the given integral as a power series. Now we have already done several questions similar to this format. So what we have to do is we just have to write down the given function according to our familiar notation, and then we can substitute this term in the power series. And also you know that this whole thing is valid when x to the power 7, the modulus of x to the power 7 is less than 1, is strictly less than 1, and that is the same as this one, right? Okay, the reason is now you can write the modulus of x to the power 7 as x to the power 7 modulus, right? So it is, since this is just the same number repeated or multiplied with itself, you will need to have this strict inequality valid for the number alone without considering the powers, right? Or else what you can do is you can take this one. Now this is equal to this one, and that is equivalent to taking the 7th root on both sides, right? So in the left hand side you will have the modulus of x, and in the right hand side you will have 1 as a result of the 7th root of 1, right? So this is the same as this one. Okay, so and then after that is just a calculation, and we have already discussed from this theorem that we can differentiate and also integrate the power series term by term. Then when you do the integral, you can see that this will be equal to this series. Now here you have a arbitrary constant, okay? But the thing is, you don't have to find out the value of this arbitrary constant, because in part B of this question we are required to calculate the definite integral. So when calculating the definite integrals, the arbitrary constant will vanish because we are doing some sort of a subtraction. Therefore the arbitrary constant will vanish, and if you need an explanation for that specific reason, please let me know. I will do that separately. Okay, right? So what you need to know is when you are evaluating a definite integral, that is an integral with these two limits, the arbitrary constant will get cancels out since you are doing a subtraction. Okay, right? So now this is the answer for part A, right? And then we are supposed to use part A to approximate this one correct within 10 to the power minus 7. So basically what we have to do is we have to evaluate this integral, right? That is this one, and that is equal to the, and so for this one we will have to evaluate it across these two limits. So we just have to substitute the limits, and when you substitute 0, the terms will vanish, and then you are left with, so when you substitute the two endpoints, you will ultimately get this one. And even you can consider 0.5 as half, and then you can see a nice alternating series as the result of this definite integral. So solving this definite integral is the same as finding the sum of this series, right? And now see the way they have given the question. We are required to approximate this integral. So approximating the value for this integral is the same as approximating the value for this series, because these two are equal, right? So now we are going to approximate the value for this series. And for this one, you can see that it is an alternating series, so we can use the alternating series approximation theorem. And if you can't remember that one, I will highly recommend you to go over the video related to that alternating series approximation theorem and first get the idea of the way that we are applying that specific theorem for the approximation. Because that's what we have to do it here directly, right? So when you write down the terms of this series, you can see that these are the corresponding terms, and since the approximation is given as 10 to the power minus 7, you can see that this term is less than 10 to the power minus 7. So from the alternating series approximation theorem, it says that if you write down the terms, now this is the term related to n equals 4, so that theorem says if you write down the first three, the terms up to this point, we will achieve the required accuracy. So since this is the accuracy, and since this is less than the given accuracy, by writing down the terms, all the terms up to this point will give you the required accuracy. That's the basic idea of the alternating series approximation theorem, right? So when you write down all these things, and of course to do these calculations you will need a calculator, right? You cannot do this manually, okay? You are not required to do this manually, right? And then once you add up these numbers, you can see that it will be equal to this 0.499 something, right? So that means now this is a very important moment, right? See, here we have found a good approximated value. Now since the error is less than 0.7 digits, right? 0.0001, right? So here we will have 7 decimal places, so it's like it's kind of a very good accurate number, right? It's not exactly the same, but it has a considerable degree of accuracy, right? So it's like without doing any integral techniques, without implementing any integral techniques, we have used the knowledge of power series and approximations, and directly we have found the value of this integral. Now remember, we did not compute this integral in any analytical way, right? We did not use any substitutions, we did not use any of those inverse trigonometric identities and stuff like that, right? But at once we have an answer for this integral. So these are some practical applications of the knowledge in power series, right? So we were able to do all these stuffs because we can integrate power series term by term, right? So first we visualize this function as a power series, and to get the integral we integrated the power series. So after that it's just adding up some numbers, right? So this is a very important application that we are using the power series, right? Without doing any without applying any integral techniques, we were able to compute the value of this integral to a very high degree of accuracy. We can even increase the accuracy if we need, okay? Right, so that will conclude the video session of this week.